Okay, well, for people who are watching this live stream, we are doing kind of a brainstorming meeting about standardizing the way that game theory is handled in Wolfram Language. And the first thing we're trying to understand is kind of a little bit of a map of what we're trying to achieve. And I think the kind of, as I understand it, and maybe you guys can sort of correct me here, the sort of the first step would be considered to be these one-shot games. And that's the first set of things, and that leads us to things like Nash Equilibrium and so on. And then kind of the next level would be some kind of iterated games in which we have a bunch more questions about having strategies and so on. Is that a fair characterization, or is that not correct?
I mean, there's strategies in both, but the strategies in iterated games include what the other players did in the past. But strategy applies to both.
So in some sense, the kind of the master function for one-shot games, if I'm not mistaken, let me just make sure I save this in the right place. Let me just try to understand. Oops, I need to.
One-shot games, I think it may be named strategy games, classical strategy games.
Fair enough, but as opposed to, but I mean, okay.
Or normal form games.
Okay. So otherwise, no. Okay, but so a name like normal form is, of course, incomprehensible to anybody outside of a field because.
Yeah, I mean, you can also just call them von Neumann games. I mean, that's sort of what the.
Okay. But anyway, the main point here is that the main function that I think we're interested in here is, am I correct? Is something like game solve? Does that make sense?
Yes,
or am I wrong?
it makes sense.
So where there's some payoff thing and there's some goal, which might be like Nash equilibrium or something, and then you are, if I'm not mistaken, what we're basically, let's see if we have some information here. Like we had this representation of, so this would be an example, if I'm not mistaken. Where essentially and obviously there are many details here about whether we have probabilities and continuous variables and all sorts of things like this. But let's walk through for sake of Jason and others what this means. If I'm not mistaken, this is kind of, if this was.
These are pure strategies. These are pure strategies, cooperate or defect. And on pure strategies, we can define mixed strategies. That is probability distributions on pure strategies.
Right, I understand. But so the first step, though, is just to understand the case where we're just the minimal case here. So this is your nice demonstration. But we're not yet coming to probability distributions because that's one different. What we had talked about. I mean,
the simplest case is you got some kind of payoff matrix, some kind of number of players. Each is picking a pure strategy, and the outcome for each person is the tuple in that part of the matrix where the three chosen strategies or however many chosen strategies intersect, and it specifies the payoff that each person receives if that's the strategy choice each person made, right? So that in for a simple one-shot game, there's a matrix.
Hold on. From a design point of view, you made an interesting point there implicitly. So if we look at a function that says, for example, minimize, I don't know, x squared plus y squared, x and y, what's that going to return? Okay, so notice that what that did was it returned two things. It returned what the minimum was, and then it returned the choices of x and y, right? Whereas in this proposed thing for game solve, we're actually not returning what the payoff was. We're merely returning the optimum. Is that correct? We're returning the analog of x goes to 0, y goes to 0.
I mean, you could return both, but what he has here is game solve with the, I mean, the Nash equilibrium being at both defect is like a result being returned. But
right, but so maybe what we should think about from a design point of view is a third argument here, where there is also the, a property type argument that determines what to return.
Sure.
So, for example, we could have. Sorry, Valeria. Yeah.
In my opinion, we must return strategies, and we may return also payoffs for strategies for players and payoffs.
Fair enough. Okay, so fair enough. So
it's
then
something analogical with minimize. We return solutions and the value of the optimal value of the function. In the case of game solve, we return strategies and also we return payoffs that corresponds to
yeah, the strategies are closest to the values of your x and y variables here, and the
yeah, right, but which is different. So arg min would be the analog. So the analog of arg min would be to return defect, for example. The analog of minimize would be
yes, defect, and also the result of payoffs.
No, I understand, but that's not what. If you're looking at the screen, right? So we've got minimize here. And minimize is returning both. So what I'm suggesting, which gets both cases, right, is that we could return here either, okay, so the default, let's imagine, okay, let's look at this. So the default, but we've got many different things to look at here. So the default case might be to return just the strategy, just the optimal strategy. Okay, now the next case might be to return a list of, but I'm not sure this is correct, a list of strategy, payoff, right? And so there, what we could do in that case is we could do one of two things. We could either say one arrow defect, 0.67 or something, 2 arrow defect, 0.4, or, which I think would be a better thing to return, we could return for this, we could return an association even. This is something that we're increasingly doing, where we say strategy arrow, and then we give this.
Stephen, I do not understand. You are talking about mixed strategies in this case.
No, this is not mixed strategies. He's just saying that we want to return a strategy outcome vector and a payoffs outcome vector as in an association. So you can look it up by saying, what were the strategies that were found by the solve? What were the payoffs that were found by the solves? And in either case, you can ask for it by name instead of by position.
That's all I'm talking about. We're not at mixed strategies yet. We're gonna tackle mixed strategies in a minute, because I think I'm just dealing with the analog of the return of minimize versus arg min.
Okay.
That would be my suggestion for how to do this. Do you have comments on this? Roger, do you have a comment on this?
Yeah, so for optimization, we had 3, there's even min value as well. So there's the triple.
So wait a minute. So for optimization, what are the cases? What are the things?
Min value.
Min. Oh, I see. The function min value.
In those cases, we didn't do. I think it's the proper thing to have the third. To say what property is it that you want out.
I think so, because I don't think
in these cases it makes more sense to have these as we did it actually. So it's not a bad design, because those are well established. And
I agree, because they're part of a pipeline, whereas I think here the likelihood of this being part of a pipeline is considerably lower.
Right.
Okay, so we're going to talk about mixed strategies, but before we talk about mixed strategies, I want to talk for a minute about iteration. Okay.
Okay.
Because I think iteration is, I think iteration is going to force some aspects of this design.
Perhaps, but before we get to that, I just want to mention one other thing here. Right now, you're talking about game solve, where you're asking for it to find a Nash equilibrium, right? You in principle could, have other things that you want to ask about a game besides where its Nash equilibria are.
Yes, but such as, I think we've already listed some of these, and I think Valerio has some of these, like best response.
Yes,
that
yes. We can ask also about max-min and solutions in the case of game solve. And also maybe it makes sense to have a function like game solve value about payoffs.
No, but that's what we're dealing with the third argument. We don't need
Yeah.
a separate function because we've got a
Right.
third argument that specifies what.
I think you're clear, Stephen, but the thing I want to point out about goals, right? There are some assumptions being built in here about the kind of game that you have, like Nash Equilibrium assumes that you've got like simultaneous choice, right? And that's one of the parameters that these even one-shot games can have is, do the players choose their strategy simultaneously in ignorance from each other? Does one of the players go first and the other player gets to react to it? There's different kinds of even one-shot games in that respect.
I see. But wait a minute. So we can think of this as generalized.
Yes.
If I slash game types or game, and how would you characterize it?
Game features, game characteristics, because this is something you want as a solve, right?
Mm-hmm.
There can be specifications of the game besides its payoff matrix, like other characteristics of it. The rank of the matrix tells you the number of players, right? But there's other aspects of the game, like is it a sequential game? Is it with what move order? Is it a simultaneous choice game, right?
Okay, so we could imagine, for example, an option called game structure, perhaps. Is that reasonable? I mean, are these things nameable or are they not?
There's not that many of them. There's not that many.
What are they?
Move orders, how much they can know about the other person's payoffs.
Okay, let's down. Okay, order of moves. Okay, amount of knowledge.
Right. About other players' payoffs. There's some other in some of the more advanced games. There's questions about whether or not. So this is, if you're asking about Nash equilibrium, for example, this is more of a property, but you can ask for equilibria besides Nash. Nash means only one player gets to change their strategy, but you can ask for an equilibrium that could be that if three players could change their strategy at once, for example, if various kinds of cooperation are possible.
So wait a minute. So Nash equals only one player can change at once. Is that right?
Well, a Nash equilibrium is one where no player can improve their performance,
right,
if all the other people keep where they are, right?
Yes.
But it might be possible for both of us to improve our performance if we could agree that we're both going to do B. I
see.
Right?
Nash, only one player is able to make a change. Optimal with respect to only one player being able to make a change.
From what he assumes the other people are doing, as min-maxers themselves. But yes, you're only considering changes that don't get to be strategic cooperation between the players.
Right. So you're saying Nash, I mean, it's basically equilibrium with cooperation of some kind.
Well, Nash means that only one person gets only one person can try to change their strategy, and if no player can unilaterally change what they're doing and improve their performance, you're out of Nash equilibrium.
I get it. But so you're saying there's some form of cooperative equilibrium where multiple players can.
There's more in games with large number of players. You can have a minimum coalition set, and you can talk about, instead of a notion of Nash equilibrium, you talk about a coalition equilibrium.
So Nash sounds like not that, Stephen.
No, but it's optimal with respect to only one player making a change. So
That's
this is the alternative case.
Okay,
this is the alternative case.
I didn't realize.
Okay. And to be clear, in Nash, you do consider over all players, no player is able to improve, but each player only gets to try to change what they're doing once. It's not a Nash equilibrium if there's one player who can improve by unilateral action. So you do have to iterate over each of the players, not iterate. You have to count over each of the players to see if any of them can improve their position.
Yeah,
they can't. Equilibrium, but they can't acting alone, right? Whereas if you're allowed to form a coalition to change your strategies together, that's a stricter notion of an equilibrium than a Nash equilibrium. If something is still in equilibrium in that sense,
I get it. Okay. So for our purposes, I mean, so you're defining various different. These sound like various different goals for the game.
Yes.
I think that we can say in Nash Equilibrium about satisfaction. Every player after the game has a satisfaction that it is not better. It was not better strategy for him to play.
Yeah, I get it. Right. Yes, but the question is,
it's a solving goal to find those. That's the way to think about it, is that it's a solving goal.
right. And there are other goals you're saying,
Yes.
Jason, which involve some kind of cooperative equilibrium.
Yes, there's stricter notions of equilibrium than Nash.
Okay, fine. But what I want to understand here is in the parameterization of these things, do you have to say players A, B, and C can form a coalition, but D and E cannot, and stuff like that? Or is that?
You usually don't. You just talk about there's the usual parameterizations, either Nash one at a time, or only N players can collaborate, or any number of players can collaborate.
Okay, so then we're going to need a parameterized version of this, right? Because if you're saying,
Stephen, other name for a name for such game is non-cooperative games. That is, cooperation. It's not possible, or it's not supposed in such games.
Right. Okay. So what we probably want to do is the goal. The simplest case of the goal is just something like Nash Equilibrium, but the more complicated case of the goal is to have a whole association which includes cooperation, move order. Perhaps we can put it in there, maybe.
Yeah, and if you want to make this as general as possible, even things like whether or not you know the other person's payoffs when you're choosing your strategy, because they're very old versions of this, which even precede formal game theory, where you weren't allowed to know the other person's payoffs. You only got to see what they were doing. This is back in 19th century economics, but that's kind of a degenerate form from the standpoint of.
Right, but I like this from a design point of view. I mean, what we're trying to do here is we're trying to get the big picture of the design, and then we'll worry about how it's implemented and things later. But what you're basically saying is that the goal structure, there's a simple, I just want the Nash equilibrium, and then there's a more complicated, let's characterize exactly what we're trying to get out of the thing.
But that sounds like constraints rather than goals.
They're not simply constraints. I mean, because it's the characterization of the kind of equilibrium that you found.
Right? Well, okay, so whether we call it goals, I mean, this is sort of objectives, what we're trying to solve for.
Yes.
That's sort of what we're talking about here, I think.
Yes.
Are you allowed to cooperate or not? That sounds like
so some of those can be, the thing about cooperation or not is some of those can be thought of as characteristics of the game itself, and others can be thought of as characteristics of the solution set you're looking for, right?
Right. So
you
I'm a little concerned.
It's the game which no cooperation is possible at all, in which case that parameter doesn't matter, right? That's just restricting the kind of.
Right. That's what I'm saying. It's the constraints. It's restricting.
Right. Okay. So look. In some cases, right. Okay. So we've got two different things here. Feature of the game or feature of the desired solution.
That's right. That's right.
And I'm afraid that will hang us at some point if we do this wrong. And arguably the best way to handle this is to have a second argument that is simply that could break those apart if necessary in the association. That would be my suggestion. Given that these are fairly close, we could potentially have,
To me, like the payoff matrix looks like the objective function in a regular optimization, and these other things.
Yes.
But Roger, I mean, one of the questions from the point of view of design. Okay, so another form of design. So there will be an alternative design in which the way it works is to say game solve of payoff, arrow or payoff matrix, arrow, blah, 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 and then constraint one, constraint arrow, blah, blah, blah.
Right. And then other things that you'll get people wanting to do.
But then those constraints might be just that. Can you cooperate?
I understand, but so my question is, Roger, my question is really, it's simply a question. Do you try and puff out the specification in the first argument that was previously just a payoff matrix and put some of this other information there, or do you put it in the second argument as a what to solve for type thing? Right? And the question is there a bright line between a specification, quotes, of the game versus a specification of the desired solution, or are those two things kind of, do they smoosh into each other?
Right.
Okay. And I mean, I don't know this field, as you guys well know, but as I'm listening to you guys, it seems to me, I'm not certain whether there's a bright line distinction between those two things.
I think they can smush into each other. I think people think about them both ways round, and they try to distinguish sets of things they're solving for by classifying characteristics of the game itself.
Okay, so that suggests probably all this stuff in the second argument.
I would agree.
Leaving the first argument as a fairly pure payoff matrix.
Yes.
I think that's right too.
Okay. All right. So can we make a little look forward before we come back to mixed strategies? Let's have a little look forward to iterated games. Okay.
Sure.
Stephen, I
Yeah.
propose to return to minimize and to do an analogy to games. In minimize, we may have two functions, one for every player, x squared plus y squared, and the second function, payoff function for the second player, and we can have as argument X and Y, we can have also the descriptions of strategy sets. And so it's an analogy between game solve and minimize. We'll, in game solve, we may have two functions, one function for every player, and also we have the same number of arguments, strategy, and the strategy sets. Strategy sets may be constraints in game solve. And about cooperate in the case of this example of prisoner's dilemma, we must understand that cooperate do not mean that this is a cooperation game. Cooperate in this case means,
we understand.
means only mutually cooperate. They do not have between them any talks and any contacts.
Right. I mean, it's just a name for that strategy. It's not.
Yes, it's
not,
the name for strategy.
Right, but I want to understand what you said about this. I mean,
yes, we may choose minimize one payoff function, one x squared plus y squared, and the second payoff function may be x x plus y simply. And so we have payoff function. After that, we must describe strategies of the players. So we have X, the strategy of first player, and for this strategy, we must describe the strategy sets. So we can write X in X element of yes, where X is strategy set, and it may be defined also as constraints. It's usually not so defined in traditional textbooks or monographs, but we can do such description. And also for the second player, we can describe his strategy and why.
Yeah. Right. But so I'm trying to understand. What you're saying is this some nonlinear generalization of the traditional minimization of game theory?
Yes. We can look at minimize at game solve as a formal or abstraction or generalization extension of minimize, but in some
I think you can often see it as you maximizing some variables and minimizing some.
About minimize, so one player may only minimize partially his payoff function because he has only he can influence only his variable or strategy. Only as example, first player may influence only x squared. He can't influence y squared. This is difference between minimize traditional optimization and game theory optimization, is if you can say so. Every player can partially optimize his payoff function, and they all can influence all the functions at all.
Okay, well, let me just try to understand. So first question, the existing structure for game solve proposed in this way, is what's being said here that, that this is not, that this is not the most general possibility because you can have an arbitrary function rather than having the standard linear algebra type minimization. Is that the point here?
It's sort of. I mean, what he's saying is that the payoffs don't have to be in the form of an n by n payoff matrix where people are choosing, an equal number of strategies each. You can have one player can choose that this variable lies between this range and this range. Another player chooses that this variable lies in this range and that range, and so forth. And the point is, if you generalize that form, then the function that's determining payoffs might not simply be a extract which column vector from a payoff matrix. It might be a more general function than that ties together the strategy choices of the players. So the point he's making is that the way in which the simple form, the von Neumann form, is that you just have an n by n whatever matrix, and people are just selecting rows and columns out of it, and the intersection of all their choices is with one cell in that, and the payoffs are listed in that cell.
I get it. Right. And the same issue is coming up to some extent in the mixed strategy case, because in the mixed strategy case, you don't just have a single, you've got some like interval of possibilities and things like this.
You have Pauli distribution over your strategy set. That's right.
Right. So what you're saying is, so let's understand what this means from in the standard way we do things, we have solve and we have reduce, right? And these are things that give us different, in one case, we are trying to nail down the minimal, well, in the case of solve, we're trying to get the generic result. In the case of reduce, we're trying to get something more complicated. I don't know whether that's analogous here.
I mean, I think you want to have a form that allows a simple matrix and understands it as in the linear form, but you probably also want to have a more complex functional form where the specifications are.
So the next case is functional specification of payoffs.
And strategy. So I want to just make another point here about the strategies, though. This way of listing, each of the players, as a dimension, so to speak, their strategy set can get more complicated when you're talking about n players of uniform strategy choices, right? I mean, if you've got 2 or 3 dimensions and they have very different controls, this way of specifying it's the way you want to do it. But if you're trying to say I'm doing a 20-player game and they all have the same strategy sets, but this is the functional form that the payoff has.
Right. So the next case is compressed.
So the array form would be an n-rank tensor.
That's right.
Players, right.
Okay, so hold on a second. Compressed array form of payoff matrix, of payoff tensor. basically. So
Yes.
one case is the flattened, you know, outcome arrow value, basically outcome 1, arrow value 1, right? And where each outcome is a complete outcome, right? The other would be the other is a you know a rank n array, rank n tensor, basically rank n array, in which right, I'm not quite sure how you label that. How do you?
So quick question: Are you talking about the outcome, or are you talking about the specification of the matrix of the payoff form itself?
I'm specifying the payoff matrix here. So what I'm saying is, in this case, obviously, this thing is really much more elaborate than it needs to be, right? Because in fact, the only information here is a matrix.
Correct.
Well, actually, it's 2 matrices here.
It's a tensor that's a 2 by 2 matrix with a pair at each point, right?
Right. So it's a 2 by 2 by 2 creature.
Yes.
But in general, it's an n by n by n creature.
If all the players have the same number of strategy choices each.
Yes.
I see. Okay. Okay. Okay.
If different numbers of choices in their strategy sets, then it could have n by n by the payoffs at the bottom have to equal the number of players in the lowest rank of the 10.
Yes.
You have to specify a payoff for every person. That's the only constraint on the form.
So n by s, but the s does it have to be a full array, or can it be a ragged creature?
It may be n by m by k by j, and
so the n is here.
has,
The n is not the people; it's the number of strategies.
yes,
That's right. So strategies of player 1.
maybe
Yes. Strategies 1 times strategies 2.
number of strategies.
Yeah, right. N strategies 1 by times n strategies 2.
And then the very last one is the number of players.
And n is the number of players.
Right. Okay.
The last one has to be equal to the number of total things you have in the previous multiplication, right?
No. In this case, we must have a tensor n strategies 1, n strategies 2, and so on, n strategies n. Number of strategies of player n.
Okay. Well, so my question is this an array where it is a genuine array that is essentially a rectangular object, or does this last index have a different range for different choices of the first 2 indices?
The last index has to have a dimension that is equal to the number of things in front of it. If it's n by n, then the last one's 2. If it's n by t, then it's 3. If it's n by s, sorry, n by n by t, then it's 4.
I see. Okay, so this can be an arbitrary rank. Okay, fine. So we need to know what this looks like, and if there is labeling on it, we need to know how that labeling works, right? So there is a raw array. There's a raw. I mean, this is probably a data set, basically. It's an association.
Right. The thing was just a little bit simplifying, though, about this. I mean, in the most general form, some of these things can be complicated strategy sets, but normally it's just, a number between 1 and n, and there's no other differentiation between them if you're talking about the actual matrix form of the specified payoff matrix. If there isn't a functional form there, then the strategy sets are, just range n.
Okay, well, all right, but so look, one of the sub branches here is to work out what this compressed array form of the payoff tensor looks like, right? That's one
When
of
you
the
say compressed?
Well, I just mean, okay, the array form of the as opposed to
Listing out A has all these strategies,
to
and B,
unrolling all cases in a list. You know what I'm saying, Roger?
Yeah.
I mean, we've got a bunch of functions that do this. Okay, so and this functional specification of payoffs, let's just address that for a second, and then I really want to go on to iterated games, because I think that's going to inform how we do some of this other stuff. the okay. So actually, there's a question on the live stream about board games and things like that. Swede, could you find the summer school projects about chess and about card games?
Certainly.
Stephen, I was to write a simple example as 3 players.
Okay.
The first player has 4 strategies. The second has 5 strategies, and the third player has 2 strategies. And to write the payoffs of such games, payoffs of every player, and so we will have a clear image of what.
Yeah, that's fine. Yeah, okay. So you're saying, but that we're talking now about the
Let
array.
us talk
Yeah, okay.
about 3-player game.
Okay.
So we have n equals 3.
Okay, so let's actually write out what the thing is. So one thing we have in the standard way of doing this, what we would have here is, so let's look.
The set of players. The set of players, it may be number 1, number 2, number 3. Number 1 for first player, number 2 for second player, number 3 for the third player.
Yeah, I understand. Okay, but I mean players 1, 2, 3. Look.
Okay. After that, for player 1, we may say about the number of his strategies.
Well, let's call them. I mean, for our purposes here, we can just call them S1, S2, S3, or something. Strategies.
Right, and he might have 2 or he might have 4. He doesn't have to have the same number of players.
Okay,
but he has
so just are you trying to write out this structure for that case? Is that the point?
I was thinking we should just do the array, just symbolically.
Okay, all right.
Symbolically
Okay, so tell me what the array looks like. So, well, actually, do you want to do the unrolled case first or the array case first?
The array case first.
Okay, so tell me what it should say. Jason, do you? But let's do the prisoner's dilemma case.
We can just do it with array, the function array, to generate it.
Yeah, I understand, but I'd like to talk about the prisoner's dilemma case, okay? Because what I think the prisoner's dilemma case.
It's 2 players, 2 strategies each, and because there's 2 players, the payoff number is 2. So you have 2 strategies each, means the first thing is 2 and the second thing is 2, and the fact there's 2 players means that there's 2 at the bottom of the tensor.
It's that's the
yes.
That's the case, right? So that's the that's e.g. prisoner's dilemma.
Yeah, any 2-player, 2-strategy game.
Okay. However, I would like to point out that this does not contain the labeling we need. See what I'm saying? So that doesn't say that right now here it's fine, but we've got strategies 1 and 2.
Yeah, it's not stored in it.
Right now it's just purely positional.
Right. So what I'm saying is we need a way. So which level of this tensor is the names of strategies? It's the bottom level of the tensor, isn't it?
No, the top levels of the tensors are the strategies of the different players, and the bottom level is the payoffs.
Okay, but so if we were going to decorate this, if we were going to turn one layer of this into a into an association
table form and put in labels so we can see it actually. Table form has labels.
Yeah, okay.
You take that array and now let's look at
table headings.
Yes. And so then it would be strategies 1, comma, strategies 2, comma, payoff.
That wasn't very helpful. Why didn't it show the table headings?
No.
The lengths don't match.
What's that?
I said maybe the lengths don't match.
No, this is. Oh, look.
Oh no, they don't. Right.
Why?
Yes.
Okay. So what are we actually trying to do here?
They need to be sublists. So there's.
So what do the sublists need to be? You tell me what is this?
There should be two in each.
Okay, so
Each string there should be two things.
okay, so what are those things? So the top level is what?
It's the player one choice, a strategy one or strategy two.
Okay, so that one is basically, let's write it in a very player is one.
I doubt that will work. The association, do you think?
Strategy is
It's
one.
fine. It'll just and the strategy is let's strategy is one.
Yeah, or A, whatever. Yeah.
Yeah. Okay, so that's one case. So now the next case is it's I mean, we can obviously do this programmatically, but let's just do it like this. So this case here is player is one or player is two?
Player is one and strategy is two. Top level.
Okay. Okay, so next level is
Just
the
player
next
two.
level is the same thing, but for player two. Okay, and the third level is what?
Payoff of player one and payoff of player two.
No. For player three, I propose to.
No, we're only doing the two by two
we're
right
doing the two by two case.
Okay.
Okay, so
Payoff function. Payoff function.
No.
Matrix.
The third level is a name, has to be
the name of the element in a cell at the lowest level of the tensor is what you're looking for. Yes.
Yes, that's right. That's what I'm looking for. So it will be cooperate and whatever it is. It's the
No, that's the name of the strategies. That's the name of the
Okay.
strategy. That's
so
what you have
what's
a
at the
strategy one,
lowest level
strategy-
of the tensor?
The lowest level of the tensor is the payoff of player one for that set of choices.
Yeah.
Okay.
Payoff of player two for that set of player
Okay.
choices.
Payoff
Payoff to
for-
one or payoff to
payoff
two.
one. Okay. Payoff to one. Payoff to two.
Yes.
Okay. All right. Huh, that's unimpressive. Oh,
I
well,
think
that's
that
because
is your array actually the right thing?
I just want to
my
work
array
those-
is the wrong shape, but it's close. Ah, there we go.
There you go.
Okay.
Yep.
All
Yeah.
right.
Okay.
Okay. So now, okay, so it's pretty clear how we generalize this. It's pretty clear. This is we can see that what we have to do, if there is three strategies for player one, we'll have a 3 by 2 array, et cetera, et cetera, et cetera. This makes it fairly clear how we have to generalize it.
Agreed.
So the only issue here is that there is a need for labeling like this that we need to think through. Okay, but let's not deal with that right now. Okay, we're not. If there's something quick to say about functional specifications, we could say that now. Otherwise, I really want to go to iterated games because I think that's what's going to.
Yeah,
okay.
let's go to iterated.
Okay, fine. So let's talk about. So what does it mean? You know, I was mentioning before I read. Yeah, go ahead.
The main thing it's going to mean is just that instead of having a single strategy for each player, you're going to have a strategy vector for each player for n number of moves of the game or t number of moves of the game, right? They're going to have a different element of their strategy set at each of the steps of the game up to t, right? And that's the specification of their move vector, and they get a payoff for each step of the game, and they have a cumulative payoff for all the steps of the game, right? And then the issue with strategies is that in general, their strategy on later moves can depend upon their moves and other players' moves on previous moves.
But the first question is,
you're just specifying the actual game instance as opposed to the game you're playing. But the game instance is a move vector for each player.
Okay, question. In the workflow, so as I mentioned to you guys, I ran into Bob Axelrod a couple of weeks ago, who is very much an iterated games fellow, and was asking him about what people actually do with iterated games. And I guess one of the questions that I have is, is there in fact, so just to lay it out there, right? And I'm confused by this. Is it the case that there is a game solve is a kind of game optimization? And is there a different thing that people do with iterated games?
Yes, yes. In iterated games, players know about the result of precedent.
Yeah, right. I understand. But in terms of what people are trying to achieve.
But there is an analog thing for optimization. It's called dynamic optimization. And that's when you do many steps. Do you see what I'm saying?
Right. And there's multiple forms. Sorry. There's multiple forms of this in terms of the time dimension and whether you have a discount on it, and do you have the infinite time case or the finite time case, and
sure.
If you have a long time case, do you have a discount factor on it? The infinite time case is a large discount factor. It can be approximated by a finite game and so forth. But there's all kinds of complexity in the way that you lay out the time dimension. And then in terms of people's strategies, just as they can have pure or mixed strategies in a one-shot game, you can have pure or mixed strategies in a iterated game, and the strategy you do next may depend upon your whole pass move vector, the opponent's whole pass move vector, those with only a finite look back in terms of the number of moves before you can consider, and so forth.
Okay. There's lots of hair, but the thing I want to understand first is the overall workflow. Like in the case of game solve for a one-shot game, I think I understand that the overall workflow is an attempt to find out for all the various players in the game what is some kind of optimal point. But is it not the case that with iterated games, there is a different workflow that is also of interest, that is more like essentially just running the iterated game, as opposed to trying to find
instead of game solve, there's game simulate. Right?
Okay.
Just run this game with players having this strategy or this strategy choice mechanism. And you can do that in the one-shot case too. It's just your game simulate is really simple. You put in one move for each guys, and you evaluate the state of the game. It gives you a set of payoffs. But game simulate, or game solve is different from game solve.
Okay, that's what I thought. Okay, so is it the case that there is a game solve? Should it be? Is it analogous? Is it directly analogous to game solve? Is the iterated game solve directly analogous to game solve?
Only in certain cases that are particularly simple.
Okay, so you're saying, I mean, clearly there's a lot more hair that you need to specify for iterated game solve.
Yes, but there are games that are purely solvable by backwards induction methods or by Nash methods, even though they're iterated, right? Especially a finite iterated game, right? They're Nash Equilibrium finite iterated.
Okay, but I'm trying to get the overall workflow here. So the question is, there is one case is simulating iterated games.
But for instance, in optimization, there are things like dynamic programming from Bellman. Okay?
Yeah.
And it means that you can, in principle, solve it. And if it's all approximate, you can really solve it.
Right, but I'm just asking. I want to understand the overall workflow, what you're trying to achieve.
No, but what I'm saying is that then you can give the whole solution to the end.
But here's the point. There's sometimes you want a solution, sometimes you want a simulation. Depending upon how simple the thing is that you're simulating, it might have findable solutions or might not have findable solutions, right? But there are times when game solve makes sense on an iterated game, and there's lots of other things you want to do with it. You want to simulate it as well as potentially solving it in the simple case.
That's what I'm.
You do want to simulate it. Yes, you do want to simulate. So even if you come up with some optimal strategy, you want to compare that to sort of a different way of arriving at the strategy. How much?
The other complexity here is what is the optimal strategy can depend upon the assumptions about the people you're playing against, and so there's all kinds of other things that go on once you're talking about actual iterated games and the way people care about them. There's the population that you're playing him against. And
right, I understand. So for example, if you know that player one has a certain strategy, right? Then your strategy, then you might want to optimize over the strategies for player two, given a known strategy for player one.
Right. So the classic example of this is, when people looked at rules with different lookbacks, they originally thought that tit for tat, doing what the other guy did last in iterated prisoner's dilemma was an optimal strategy. And then they discovered that if the rules were restricted to only look back one, they were too stupid to learn from tit for tat, and permanent retaliation works better than tit for tat. because the rules are so stupid they don't adapt to being taught by tit for tat, right?
Yes.
So it depends upon how sophisticated the strategies are that can be adopted by the people you're playing against, what the optimal strategy is for you.
Right.
So because they want to be able to consider it things like that, you want to be able to simulate, and you want to be able to game solve under, it's not just constraints, it's game requirements. The strategies have to be from this set. The solutions can't look back longer than this. The game doesn't go on longer than this. There's various kinds of constraints you can put on it to make it something you can solve.
Okay, but fundamentally, in this iterated game optimize, the result is a function that tells you what to do. Is that right?
Well, it's going to tell you strategy sets to the players that meet the criteria that you set, right? Which could be that this is an optimal strategy against this other player set, or that this is a Nash equilibrium of all of these strategies, or that this is, you're going to be able to ask different questions.
Yeah, I get it, but I'm trying to understand a different issue, right? In the case, in the game solve case that we had up here, the fundamental answer, at least in the pure strategy case, we'll talk about the mixed strategy case later, right? The fundamental answer is a particular strategy or a set of strategies.
No, it's a set of strategies. It's a strategy for each player and a payoffs for each player.
Well, we don't necessarily return the payoff. We're not necessarily returning the payoff.
I understand, but the fundamental thing is a set of strategies that meet the criteria that you asked for, like that they're a Nash equilibrium.
Yes, I get it. But what I'm trying to understand, in the iterated case, it seems like what you often want is to come up with a black box function that, given certain characteristics of the game, will be, that's much more like a control systems problem, I think, where you're trying to get a black box function which, given the characteristics of what's happening in the game, will somehow optimize things for you. Is that correct?
The only problem with that is the for you aspect of it that you're repeating there.
Well,
right?
okay, fine, but it doesn't necessarily. But so
I want to differentiate between, if you're asking for a for you, what you're effectively doing is you're fixing characteristics of the other players. You're letting one of the players vary a strategy, and you're asking what he can optimize, right, by doing that, right? There's a whole set of questions like that. But they're not Nash equilibrium questions.
No, I understand. So there's different criteria, but the fundamental thing from a workflow point of view that you want out of this, if I'm not mistaken, is a function which, when given, a thing you want out is a function which, when given the history of the game, tells you what to do next.
Not necessarily. That's a strategy rule, and you might want that as an input, or you might want that as an output.
I understand. That
could be an input when you simulate.
It could even be an input when you're solving.
Yeah, I get it. You know some player's strategy, but the output you want is find me a strategy which is somehow optimal given the things that I know.
I understand. My point is that strategy that is optimal might just be a move vector. It might not be a formula that looks at the past to tell you what to do next. It might just be do these moves for the next, this actual list of move choices.
So your point is, okay, and that's the case where in the one-shot game, that's all you have.
Stephen, you can look at such game as one-shot games. We can look if the number of iterations are infinite. You can look at these iterations, strategies as sequence, and we must find limit and of such payoffs, maybe sums of payoffs, but in such case there is a multiplier that tends to zero.
So I understand. Then there could be a discount rate and so on.
This make sense for such game, such infinite games, to have a solution. But in the case when we have a finite number of iteration, in my opinion, it's not so interesting because we have a vector, and we can look at such a game also as a one-shot game.
I get it. Yeah, for a long sequence, right? A one-shot game
with a huge number of strategies. The point he's making is that
yes.
you can think of 8 choices of 1 and 0 as being one choice of 2 to the 8th possibilities.
Of course.
Yes,
right.
yes.
Right.
So theory in such case is more developed in for sequences, infinite sequences, but for finite sequences, there is a lot of so-named experimental games. There is also a branch of game theory, a branch of experimental games. For experimental games, there are a lot of interesting results that looks not so good as in theory.
Right.
Or
Okay.
theory not looks so good as
okay, but I want to understand. I'm trying to understand the workflow of what people want here.
Right.
So,
and I'm trying to say that I think that for Game Simulate, you want to have the idea that there's an output which is just a set of actual choices of moves for the different players, the different steps of the game, right? And payoffs occurred along the way. It's kind of like just the nest listed or the fold listed version of what you had for the one shot, and it's leaving behind a trail of states of all the choices people made, right? And it's just those move vectors. That object is the game instance, right? Of the choices were made. These move vectors were put in at the different stages, and you can ask characteristics of it, like, you know, what's the sum of the payoffs of all the players?
right. So one possible way to do that would be to have a game solve list. So game solve is the one-shot case, and game solve list, I don't know if this is right, but that will be a possibility, or iterated game solve.
Right, but before you even get to the solve, you just want to have the thing which is the instance, right? You want to have the data object, which is the instance itself, which could be game evolve list or something like that. But it's not necessarily solving or optimizing anything yet. It's just this particular set of moves with this original payoff matrix, right? The character, and that is leaving behind a set of characteristics as a
but
data
I don't
structure.
understand why it. What? Okay,
I'll tell you why. Because
the next move, Jason. How do you pick the next move?
This is my point. You can either have it be something which is laid down in advance. You choose your whole move vector, or you can have it be something which is a function of the previous moves. Those are two different ways of arriving at a strategy choice.
Right, but if it's laid down in advance, there's no evolution happening. It's just
the evolution in that case is just a set of payoffs that occur, right? But my point is, you want to think of the other strategy choice things as ways of specifying every player's move vector.
I think we can return now to prisoner's dilemma. There are a lot of competition for such games, iterated prisoner's dilemma. And for such game, one of winning strategies is do so as your opponent in the precedent iteration.
Yeah, tit for tat, we know.
Yeah.
And in such case, we have other type of strategies. We
right, but I'm trying to understand if in that case, let's take the tit for tat behavior in the iterated prisoner's dilemma. Okay.
Yes.
What we want. So one function that we want is something that just says, you know, do tit for tat.
Yes.
Right.
And show what happens.
Right. So
yes.
Stephen, when we were doing some of these game theory experiments in some of the previous projects, right? We would have a data structure which had the move vectors different players laid down, and then we would have a function like a rule that determined
yes.
what you should do next, and that could be specified by you can only have a look back list of this far of your own and the other guys, and then you can look at all the possibilities. And tit for tat is just the one that has for all the different possible look back one things. It just happens to pick its next move, like the coloring of a CA rule, by only what the other person did last, right?
Okay.
But that's just of an all possible combinations of your moves and the other guy's moves as far look back as you have. That right arrow, I do 1, right, or I do 0. I do what he did. But that's just like a CA rule. It can have a dependence on any of its predecessors, right? You just specify the rule that way. But that specification of the rule is different from the actual sequence of the moves of the game. It's just what's determining the sequence of moves of the game.
I get it, I think, but what I'm saying is you could imagine something where at every step you effectively do a game solve with a certain goal. That's one possible way of doing this. It's not the same as tit for tat. Tit for tat is doing something, it's a particular strategy that ignores the whole game solving thing.
Sure, it doesn't look ahead at all. It only looks back.
Right. So, but what I'm trying to understand, again, let's go through this again, okay? The output that I want here, I would assume, is given a game history, right?
Yes. Game history, and maybe some of the payoffs in every iteration.
Well, but
or maybe
look,
other.
What I want is something which says, okay, fundamentally, what this wants to say is, whatever it's called, game iterate, game simulate, whatever. I think game iterate is the right term. So for player 1, their strategy function, they have a strategy function that gets to look at certain kinds of things, and player 2 also has a strategy function, right? And these strategy functions are looking back. They can look at a bunch of different stuff. They're fed a bunch of different things. And then what game iterate has here is some kind of history vector, if I'm not mistaken. And its result is a next move based on those strategies. Is that right?
Well, I mean, it doesn't have to be a next move. If you've got the functions and you have the past moves, you can just put an end there and do as many steps as you want, right?
Fine.
One strategy may be to generate randomly the strategy of...
Sure, but that's fine. That's just what these strategy functions do. Right?
So
the strategy function could be anything. I mean, this is basically saying, okay, so this would be game iterate list effectively, and this would start from a init and then give you move 1, move 2, etc. An init could be something that is more than one. It could be a little piece of frozen history, just like nest list can look at multiple. If I remember how this works, we have a nest. What is the function that can look back more? Nest list doesn't need to look back more for some reason, but nest while list does need to look back more. Right. So this would be like nest list. But can have a longer init vector. Is that right? I mean, this is the basic workflow here. And I don't understand the difference between this function and what is special about this being a game theory function, as opposed to just, why is this a game theory function?
I mean, until you put constraints on how when that function takes, it's not particularly a game theory function. It's just a way of generating a vector that can be interpreted as a move vector and fed a set of game payoff matrices. But the only thing that makes it a game function is the fact that function cares about the contents of those payoff matrices, right?
Yeah, I mean, otherwise it's just a general function that's just doing.
Right. That's right.
I unfortunately have to go fairly soon, and we will have to continue this at a different time. But I actually feel like we're getting going pretty well here. I'd like to understand, actually, some questions from our live stream, which I'd like to address here. There's a bunch of discussion here about adversarial learning games. There's questions about board games. I think there were some nice projects at the summer school that involved so this was an example of a card game and a specification. This is worth us looking at, okay? Because this was a specification of a card game. Am I making sense? With things like a game tree and so on. Am I making sense? And this has
in the case of iterated games, it looks that we do not have a tree of the games.
But you could have a tree. I mean, you said random.
We could have, but it's, in my opinion, more simple.
Yes.
We describe a one-shot game. Game iterate has a description of one-shot game. After that, we may describe the number. We can give the number of iteration, and we can give also a strategy for iterated games. Strategies like tit for tat.
Sure, but we want to be able to give a general strategy. But the point here is...
Yes.
The difference here is one is a random variate or something like it.
No. This game we're seeing in front of us, right? This is a different kind of thing. It's a game with a game state and a tree of that it passes through, tree of states that it passes through based upon the player moves. Whereas the iterated game setup, the only effect of the past is to control what players can choose next if their strategy depends upon the past and the payoffs that they get. But the payoffs they're getting is a per move thing that's just accumulating, either adding or with a discount function. But there's no evolving game state like there is in the example in front of you, right? In the example in front of you, you've got a different abstraction of what a game is. That the game has a game state, and the choices of strategy change the game state you're trying to reach, and they're only payoffs at end states of the game. So that's a different.
I see. So what you're saying. So in the case of the game theory we're talking about, there is no useful game state except there is a move made by each player. I don't quite understand. There is some game state because there's a move made by each player.
The game state resolves to a payoff at each step, and then and that's the only effect of each. The only effect of each round of the iteration is a payoff's experienced by all players for that step of it, and whatever influence that and their past choices have on their future choices. But it has no other ongoing recorded state that the players are controlling.
Your example, this example is related for extensible game theory. In other branch of game theory, there are a lot of results and contribution to.
Okay, but this is but your point is okay, and this is relevant.
It's
for
very
games
interesting. Function game iterate because we can experiment with such function. We can simulate.
Yeah, I understand, but the issue here is, and on our live stream there are questions about relationship to game simulators used in machine learning, for example, and the notion of reinforcement learning strategies and so on.
Right.
What relationship they have to game,
and that's closer to this form of game, the extended form of game, because what they're doing in those cases with the reinforcement learning things is they're actually hooking up an AI to the game controller of a scrolling video game, for example, and they're trying to teach it what to do in the game by how well or poorly it does, right? So in that case, they're using a game which has a state and not just local payoffs to train the AI to move the controls of the game, right?
Yes.
So they're using a long form, extended form game like this, and then they're giving the feedback to the AI of, you can move your controllers around in only these ways and fly through the simulator as many times as you like and try to learn what works and what doesn't work in it.
Right, which is a different use case, is what
Correct. Yes, that needs the implementation of an idealization of game with state, not a one-shot payoffs game of the Neumann-Morgenthau form.
Right. Well, so that's interesting because we need to understand. Okay, so we need to understand the correspondence between these.
It's very interesting to use machine learning in the case of iterated games, but in my opinion, it will not have a good result.
Okay, fair enough.
Some of them will, but I mean,
Because I don't know.
Yeah, okay. I mean, look, okay. What's the, okay, just a minute. Let me just write down, just so we have notes for next time, relationship to other stuff. And one thing we have is machine learning and reinforcement learning.
Extended form games with state.
Yes.
Okay, well, so there's games with state. You know, machine learning, reinforcement learning. We've also got the relationship, which I don't understand, to control theory.
Right. So in that case, what you want is that move function, you say, and it's a feedback function of state.
Okay.
Right.
So that's
the same idea.
What you get out. Yeah, that's what the controller is that function that tells you what to do next, depending on state.
So for instance, when we have in all that stuff we were talking about with Arduinos and God knows what else, when we've got that, just tell me what function to look up here, Roger. What function should I look up to just see?
Linear quadratic design. What is it called? LQG.
Well, isn't it? What about our friendly Kalman filter?
Well, but it's harder to explain there. It
okay.
is.
Okay. All right. So what was it called? Linear quadratic. What is it?
Yeah. I can't remember what it's called. Linear.
LQ regulator.
Yes, that sounds about right.
Okay. Design using state space models.
Okay.
I know nothing about this stuff.
Okay, so if you pick this LQ regulator gains, for instance.
Okay.
So the way that this is for linear systems, and the objective that you want to minimize is an integral of a quadratic that measures the error of what the goal is for you.
Okay.
And if that turns out, and it's an infinite time horizon, in that case, what comes back is that the optimal controller or player, if you like, will have it's just a linear function of your state.
Okay,
so that's what the gains are that comes back. Those.
Question: does this matrix have anything to do with the game payoff matrices? We probably have no idea.
No. Well, indirectly, but if you open it up, I can't remember what this note say. This was. Can you open up notes?
The answer is there is a correspondence to the
right.
to
the payoff
limit, but
the cost. It says the cost function. That's the payoff. Okay.
Yes.
See down there the integral with a sum.
The cost function is yes.
Okay. That's the payoff. I mean that's what you want to minimize.
Okay.
And that's similar to wanting to maximize the payoff function of your iterated game with an infinite number of moves. Right.
Now, tiny variations of this, like if you want to do it over a finite time horizon, it doesn't come out as a constant linear function like that. It's going to vary. And that's when you solve. In that particular case, you get a Ricardo.
So hold on a second. So what we've got here, reinforcement learning, control theory, and solution of iterated games seem like they are related.
They're absolutely related. Yep, absolutely related.
Yes.
Yeah, in this case, one way that you see your adversary, for instance, is as noise. Those are things that act on the system. It's like another player, but you can't control what they do. So the wind that blows on your airplane, it's going to blow on that airplane and you can't control it.
Okay, so in control theory, a quote player is often an external stochastic.
Right. So
Right,
for
and-
instance, for your heating system at home, Stephen, you can't control how many people walk in the room. Everyone is about 65 watts. You know,
Is
you
that
can't.
correct? I thought it was 50 watts. Is it 60?
Well,
It probably depends on how.
right. It might be 50. Okay. It's
Okay,
thereabouts.
right.
Okay.
Yeah, go ahead.
But that's a variation. That's just stochastic. You can't control it.
Mm-hmm.
Or how much sun shines on it, the irradiation.
right.
Okay.
Right, but you can statistically say something about it, but you cannot, in
Exactly.
specificity, say anything about
Right,
it.
and then there's two ways you can look at that. You can think about what's going to be the likelihood or expectation of the noise that's going to be coming in, and that's one way. And the other is you can say what's the worst thing that can happen, which is if you imagine that random environmental vector were a player trying to break your system,
Yes.
and
Yes,
so
right,
the,
okay.
the hostile player and the worst environment are equivalent.
Right, I see. Either look at statistical expectations or
Worst
or
cases.
worst case scenario.
Yeah.
Yep. And all of that happens in control. It's just we don't have functions for all this. We have sort of the simple, very production, you know, all of these other things are there too and are used, in fact.
And does I don't think necessarily we have the right people in this meeting to know this, but for in the case of modern machine learning and reinforcement learning, are they? Can you compare that to these things?
They're very similar because
Yes.
that noise vector is that other player.
And
I
they
see.
use updating schemes that are very much.
And it
like
very
that.
much comes from what's called dynamic control or optimal control.
Yeah.
Okay.
This is all the Wiener
Yep.
process control theory stuff.
Right.
No, I don't think so. You said about noise. This is nature, and such type of mathematical models are only decision-making problems. We must have another at least two rational players that influence the system.
Yeah.
In such case, we have a game.
We know that, but the idealization that people who are doing this for control theory do is they imagine that they as a controller are one player, and they imagine that a hostile environment is like an enemy player trying to break their system. And that's a way of thinking of making their system robust against the worst things that the random environment can throw at them. They treat the random environment as a hostile player, and they endow it with an intelligence it might not have in order to stress test their system.
Right. So
Yep.
one thing I'd like to understand here, and I really need to go then, is we're starting to work on GANs and other sort of different sort of interaction structures for machine learning, right? And to me, there seems to be an analogy. I'd like to make sure that we have a similar structure. I mean, because for example, we've also got the whole active classification business and so on.
Yep.
Which is
the recurrent neural networks and this stuff are going to be very, very close.
Right. So we have to think about active classification. All right. Well, okay. Very, very useful, guys. We're making progress. We're not there yet. I think we need to tackle this iterated stuff more carefully, and we also need to look at the horrifying case of mixed strategies, which I claim is going to be the reason I'm pushing on the iterated case, right? Is I think the mixed strategies are going to be a special case of what we need to do for the iterated case. Because I claim the mixed strategies are going to wind up being, some essentially random variates or something. It's not really a random variate, it's really a distribution, but it's a random variate coming, anyway, never mind.
Those are the same.
There are going to be some
Random variates.
similarities, but the other thing to realize in the game context is that there's an extra reason to use a mixed strategy in a game context, which is to make yourself less predictable to the other player. So that's the thing which is different about choosing a mixed strategy in a competitive context. Like you bluff a certain amount of time in poker because it makes the other player get less information every time you bet.
Okay, very useful, guys. To be continued. Hopefully we can continue this soon, making progress.
Okay, yep.
Thanks. Okay.
All right,
Thank
bye.
you.
See you guys. Okay, see you. Bye-bye.
See you.